In linear algebra, we learned that if we have a three-dimensional coordinate system, x, y, and z were the axes, then we could identify three linearly independent functions. In this case, normally they were I, j, and k. And these were the unit vectors where I was the I hat was equal to 1, 0, 0, and the j hat was equal to 0, 1, 0, and the k hat was equal to 0, 0, 1. Then any point in this coordinate system could be written as a linear combination of these three vectors. In other words, we found three linearly independent vectors in 3 dimensions. So in 3 dimensions, we have 3 linearly independent vectors. And then we could write every single point in 3 dimensions as a linear combination of those 3 vectors. We're going to apply this technique, or this idea, and I think it's really intuitive how we're going to do this, but we're going to apply it to the idea of a general solution of linear differential equations. So if we have an nth order linear differential equation, and we have found n solutions, so y sub 1, y sub 2, on and on up to y sub n, then if we can show that all of these are linearly independent, then that means that the general set of solutions, or the general solution of this differential equation, right? The general solution can be written as a linear combination of all of these linearly independent solutions, plus on and on, plus c sub n, y sub n. Now, there's a test that we can use to show whether these set of solutions that we have found are linearly independent. And we're going to make use of a special determinant called the Wronskian. So we have the Wronskian determinant, and it is named after a mathematician. I'm pretty sure his last name was like Wronski or something. So it's the Wronskian determinant. And determinant. There we go. So we have W, which denotes the Wronskian determinant, and we'll have Wronskian of y1, y2, on and on up to y sub n. And what this is equal to is, well, it'll be y1, and in this first row, we will just write all of our solutions. So on and on up to y sub n. Now in the second row, we're going to write the first derivatives of our solutions. So y2 prime, on and on, all the way up to y sub n prime. And we'll go all the way down to the n minus 1th derivative. So to the n minus 1, and we'll go all the way down to the n minus 1th derivative, and then likewise over here, right? So we'll go all the way down here, and we'll have the n minus 1th derivative. And note that this is a square, right? We have the same number of inputs for our entries for our rows as we do for our columns, because we have n solutions across the top. So we have n solutions across the top, and then we go down to the n minus 1th derivative, but we start with the 0th derivative. So we have 1 right here, and then right here we have n minus 1, and then n minus 1 plus 1 is just equal to n, and we have n entries across, along the rows, and we have n entries along the columns. Okay, so that is the Wronskian determinant. And essentially what the theorem states is, okay, well, if we plug all of this in and we can show that this does not equal 0, if this does not equal 0, then what this implies is that our set of solutions is linearly independent, Okay, so, and then from there we'll be able to show that the general solution, often called the fundamental set, right? This right here is called the fundamental set of solutions. So fundamental set. that the general solution is equal to the linear combination of the fundamental set of solutions. So as an example, let's say that we have y sub 1 is equal to e to the x, and y sub 2 is equal to e to the 2x. And we want to show that these two are linearly independent. Well, I believe we showed this in the last video, and it was pretty simple, but we can actually make use of the Wronskian. We could say, okay, well, that will be Wronskian of e to the x, and then Wronskian of e to the 2x. And this would equal, well, e to the x, and then e to the 2x. And then the derivative of e to the x is just e to the x. The derivative of e to the 2x is 2e to the 2x. And one technique that we can actually apply to this is, well, if it's true for any x, then, or for one x, then it will be true for all x, because these are continuous functions. So let's let our x, let's say x is equal to 0, and now we have Wronskian of y1 and y2, right? And these are being evaluated at 0, right? Then we'll have, well, that'll be e to the 0, which is 1, e to the 0 is also 1, and then we have 1, and then we have 2. So now we can find this determinant, which is a little bit easier, and then we'll have 2 minus 1 is equal to, right, because we did 1 times 2, we got 2, and then we did minus 1 times 1, and this is equal to 1. And obviously 1 does not equal 0. So since that doesn't equal 0, we've shown that these two functions are linearly independent. And now, if these were two solutions, right, we have two solutions here. So if these were the two solutions for a second order linear differential equation, then the general solution could be written as the following. Y is equal to c1 e to the x plus c2 e to the 2x. But that would only be the case if this was a second order differential equation. In the case if it was like a third or fourth order, we would have to find more solutions and then evaluate the Wronskian of more solutions to be able to show that they all are indeed linearly independent. And if they were, then we would continue on and on. For example, if we had y3 is equal to e to the 3x and y4 is equal to e to the 4x, and we showed that all of these were linearly independent, then what we would do is we would say, okay, well, the general solution now is equal to this, and the fundamental set of solutions, which is the term for all of these, the fundamental set of solutions, so fundamental set would be y1, y2, y3, and y4 for that given differential equation. I hope you found this video helpful. If you have any questions, please leave a comment below. I'll be sure to respond. Please subscribe to help the channel to grow so I can continue to post more content, and I will see you in the next video.